From now on, we want short introductions. So I have to apologize if my title is slightly misleading. What I'm actually talking about is models for predicting the sound quality of sound reproduction systems. So I'm not going to be talking about sharpness or roughness or anything like that, but characterizing the quality of sound reproduction systems like headphones or mobile phones or loudspeakers. So what I want to do first of all is to describe some basic characteristics of the analysis of sound in the peripheral auditory system, because that's very relevant for what I'll be talking about later on, these development of these models. And in particular, I'll talk about the concept of auditory filters and excitation patterns. And then I want to talk about types of distortion and to distinguish two types that are often mixed up in the literature. People don't distinguish between these, and I'll explain later on what I mean by linear and nonlinear distortion. And then I want to talk about the models for predicting the perceptual effects of these. And I'll describe some perceptual evaluations of the model, comparison of predictions and experimental results. So first of all, just a very basic thing that you'll all be familiar with, but this shows the transfer function from the free field to the eardrum. So if you imagine you've got a sound coming from in front, you measure the sound field with a microphone in free space, then you put a listener in place, you put a microphone close to their eardrum, and you measure the sound that you get in that case. And this is showing the difference between these two. So you've got 0 dB at low frequencies. The sound level at the eardrum is the same as the sound level in the free field. But around 2 to 3 kilohertz, you've got this big boost, which comes from the ear canal resonance. And so that accounts for the fact that we're more sensitive to frequencies around 2 or 3 kilohertz than to any other frequency. There's a secondary peak up here that's to do with the reflection from the pinna, and that position of that peak varies with sound direction, whereas the position of this main peak is independent of sound direction. This shows a comparable transfer function, but for diffuse incidence. And this is where you average for many different directions of the sound source, left, right, up, down, front, back, every possible direction. And that gives a smoother overall curve with a broad peak around 2 to 3 kilohertz. And you can think of this as the typical response that you get at the eardrum in a realistic situation where sounds might come from many directions. And this response is actually the target for many manufacturers of headphones. Companies like Sennheiser design their headphones to have a so-called diffuse field response. So do Etymotic Research with their ER4 and ER6 earphones. So this is considered the ideal response of a headphone for giving a natural reproduction of music and speech. So a lot of people think a flat response is what you're aiming for. A flat response would be good for a loudspeaker because this peak around 3 kilohertz is put in by the physical characteristics of the ear canal and the pinna, but a headphone isn't necessarily reproducing that kind of characteristic. But this is basically what we would aim for. This is our kind of reference target response. This shows an estimate of the transfer function of the middle ear. Now, this is loosely based on measurements from human cadavers. You carve out the temporal bone and do some measurements, so these are based on dead ears, not living ears, and may not be entirely accurate. But we've tweaked the characteristics a little bit. This transfer function actually is taken from our model for the loudness of sounds, and we tweaked it to give accurate predictions of absolute thresholds. The function down at these low frequencies is largely guesswork, but we know that the response does roll off at low frequencies, And that's probably a good thing. We evolved that way because in the environment there are many intense low frequency sounds which would have a masking effect on higher frequency sounds if the middle ear did not roll off those low frequencies. So without this, if the response of the middle ear was flat, you would not be able to hold an easy conversation in your car because cars have a lot of low frequency noise. The response also rolls off at very high frequencies, and this partly accounts for the upper frequency limit of hearing. So even young people can't hear much above 20 or 22 kilohertz because of this roll-off of the middle ear. If you apply a sound via a bone vibrator that bypasses the middle ear, you can hear frequencies up to 100 or 150 kilohertz, although they're probably being heard by various non-linearities, but the middle ear essentially is blocking the very high frequencies too. Okay, so I want to move on now to talk about analysis of sound in the peripheral auditory system. I used to start every talk with this sentence: the peripheral auditory system behaves as if it contains a bank of bandpass filters with overlapping pass bands. The concept goes back to Helmholtz and then was developed more by Fletcher in 1940. Fletcher worked for the Bell Telephone Labs, and he was trying to design a telephone system that could be as bad as possible but still give intelligible speech. So he wanted to know how much they could degrade the signal in terms of frequency range and signal to noise ratio and distortion and still have that signal understood. And to do that, he decided he needed to understand how the auditory system worked. So we call these filters the auditory filters, and we think that each auditory filter corresponds to a specific place on the basilar membrane within the cochlea, and different places correspond to filters with different center frequencies. And here's a typical shape of an auditory filter centered at 1 kilohertz. This is just showing its relative response, arbitrarily plotted with 0 dB at the tip. And this is based on psychophysical measurements using the notch noise method, and I'm sure many of you are familiar with that. And this shows our estimate of the equivalent rectangular bandwidth of the auditory filters. This is just a measure of their bandwidth, of the sharpness of tuning, so small bandwidths indicate sharp tuning as a function of center frequency. And up here, I give an equation that was developed by Brian Glasberg and myself to fit the results, and that's shown by this solid line here. And I should mention that when we developed this function, there were no data up at these very high frequencies or very low frequencies. Only mid-frequency data were available, but it turns out the function does a pretty good job of predicting results over a very wide frequency range. This dashed curve shows the function, critical bandwidth function proposed by Zwicker, and you can see that function flattens off at low frequencies. At the time when Zwicker suggested this function, there were almost no data at low frequencies. There were no direct measures of auditory filter bandwidth, and it turns out that what they did at low frequencies was wrong, was incorrect. But a lot of people in the engineering field still use Zwicker's critical bands, especially in Germany, on the basis that Zwicker could do no wrong. But I think it's time to change, and nowadays this Erb width function is more widely accepted. So Erb N stands for the equivalent rectangular bandwidth of the filters for young listeners with normal hearing, or generally for people with normal hearing. The filters broaden with hearing loss, but that's a different story. Now, I want to also introduce a scale called the Erb Number Scale, which is just a transformation of the frequency scale. You could think of it as like taking the log of frequency. It's just frequency represented on a different scale, but it's more psychoacoustically relevant. And it's based on the Erb width. So in a step of one Erb width, one Erb n, corresponds to a 1 unit step on this Erb number scale. So for example, the width of the auditory filter centered at 1000 hertz is about 130 hertz. So if we go in frequency from 935 to 1065, that represents a step of 1 cam on this scale. And we use these units cams because this scale was developed in Cambridge together with Roy Patterson and Brian Glasberg and myself, but the unit was actually suggested by Bill Hartman. And a simple formula relating Erb number to frequency is given here. Again, F is frequency in hertz. And this is conceptually similar to the Bach scale, but it's better because it's based on the right data. Okay, and in what follows, in the models that I'm going to be talking about, we transform the frequency scale to an Erb number scale. And this is very similar to a scale of distance along the basilar membrane. And each 1 cam step corresponds to a distance of about 0.9 millimeters along the basilar membrane. And the whole length of the basilar membrane is between 35 and 37 millimeters, depending on the individual. Okay, now another basic concept that I want to cover briefly is the excitation pattern. And this is a representation of the relative response as a function of position along the basilar membrane. And you can think of it as an internal representation of the spectrum of the sound. It's like a blurred version of the spectrum. And we can define it in psychoacoustic terms as the relative response of the different auditory filters plotted as a function of the filter center frequency. And here's a very simple explanation of that. Imagine that you have a 1 kilohertz tone and you want to calculate its excitation pattern. I've schematically drawn here 5 different auditory filters. Each filter is roughly symmetric on a linear frequency scale that's shown here, but the filters get wider in their Erb, their equivalent rectangular bandwidth, as the center frequency goes up. And what we want to do is to calculate the excitation pattern, and we do that by looking at the relative response of the different filters. So if we take this lowest filter, its center frequency is about 0.7 kilohertz, and its relative response to the signal is given by this point A here, which is about minus 41 dB. So that gives us 1 point on the excitation pattern. And if we repeat that for each filter in turn, then we map out these points B, C, D, and E. So this top filter, which is centered at about 1.7 kilohertz, has the relative response E, and that gives us this point here on the excitation pattern. And so you'll notice that the low frequency side of the excitation pattern is determined by the high frequency side of these auditory filters that are centered below the signal frequency, and the high frequency side of the excitation pattern is determined by the low frequency sides of these auditory filters. Now here I've arbitrarily plotted these patterns with the tip at 0 dB. In practice, you can add on the actual signal level here so that you, instead of getting 0 here, you get something equivalent to the signal level at the peak of the excitation pattern. And these are examples of excitation patterns for a 1000 hertz tone. They're now plotted on an Erb number scale with units of cams. The corresponding frequency is at the top. And these excitation patterns take into account an effect that's been observed psychoacoustically, that the low frequency sides of the auditory filters get less steep with increasing level, and that means that the high frequency side of the excitation pattern gets less steep with increasing level. Okay, so now I want to move on to the main topic of the talk, which is about the distortion produced by sound reproduction systems, and obviously the sound quality of an audio device depends on how accurately that device transmits the properties of the sound source to the ears of the listener. And I want to distinguish two types of distortion. The first one I call linear distortion, and that's really deviations of the frequency response from the target response. So in the case of a headphone, it's a deviation from a diffuse field response. And in principle, you can correct linear distortions with a linear filter. If you've measured the characteristic of your headphone or loudspeaker, then you could pre-filter the signal to compensate for that type of linear distortion. Some people don't even like to call that distortion, but it is a form of deviation from the ideal. The second type of distortion is nonlinear distortion, where you get frequency components occurring in the output of the device which were not present in the input. And that can include discrete tonal components, or it can produce noise-like added sounds. Now, these two types of distortion have different perceptual effects. Linear distortion is described by terms like bright, dull, nasal, boomy, thin, full, or coloured. But these are all things that are to do with the timbre or tone quality of the sound. And not everybody agrees on what these terms mean. But a nonlinear distortion is characterized by or described by terms like noisy, harsh, gritty, or rough. Those are the sorts of sounds of terms that are used to describe them. And I believe that these are distinct aspects of perception which you need to model in different ways. And that's been the approach that we've taken in modeling the effects of these two types of distortions. So I want, first of all, to talk about a perceptual study that we did to characterize the effects of different types of linear distortion. In this study, we presented sounds via headphones that had approximately a diffuse field response, but all stimuli were filtered so that it had exactly a diffuse field response in a reference condition, our kind of ideal reproduction system. And then we introduced deviations from that response. And this shows examples of the kind of filtering that was applied to the signals in order to produce these linear distortions. And these are all plotted on an Erb Number Scale with units of cams. So up at the top here, I'm illustrating the effect of introducing what we call spectral ripples, peaks and dips in the response, which are quite common in sound reproduction systems. They're common in headphones. You also get them in hearing aids, for example. It's quite common to see ripples in the frequency response. They're not usually regular like this, but we thought it would be interesting to include these regular ripples and make them either rather rapid ripples in the frequency domain or much more coarse ripples. And we applied them over a wide frequency range or over certain limited frequency ranges as well to assess whether ripples are more important in any particular frequency region. Then we had spectral tilts, where you might have a gradually rising response or a gradually falling response. We had spectral tilts combined with spectral ripples, and the spectral tilts could extend over a wide frequency range or over narrow frequency ranges. And finally, we had a set of conditions where we introduced what we call band limiting, where you could either remove some of the higher frequencies or some of the lower frequencies or both together. So the stimuli covered different frequency ranges. And these stimuli were all presented mixed up in random order. We used both speech and music signals. And for each presentation, we asked subjects to evaluate these sounds on a 1 to 10 point scale, where 10 was means completely natural sound quality and one means highly unnatural sound quality. And before we started the experiment, we played them examples of a stimulus without any of these spectral deviations at all, our ideal reference, and we said that's one that should sound good, that's our reference one, and we played them ones with large amounts of spectral ripple over a wide frequency range or stimuli filtered to only cover a narrow frequency range and said these are examples of ones that should sound bad, just to give them some anchors so they use the response scale reasonably consistently. So this shows examples of the results that we got for small amounts of spectral ripple. So this is a 5 dB ripple depth, typical of what you might get in a good quality loudspeaker. If you've got a loudspeaker with a response that's described as plus or minus 3 dB, you think that's a pretty good loudspeaker. So this is typical of what you might get there. And on the whole, these ripples don't have much effect on sound quality, but there are effects, and the effects are biggest when you have rather rapid ripples or dense ripples. So for these rates of 0.2 ripples per cam and 0.5 ripples per cam, that's where we get the lowest ratings. And especially when the ripples occur over a wide frequency range, here from 87 hertz to about 7,000, and you get a smaller effect if the ripples only occur over a limited frequency range. This is what you get with larger spectral ripples with a 15 dB peak to valley ratio. That's what you might get in a very cheap pair of headphones or a pretty lousy loudspeaker. Now there are much bigger effects on sound quality, but again, you get the biggest degradations when you have a high density of ripples occurring over a wide frequency range. And generally, we found that ripples at high frequencies had a less degrading effect than ripples at low and medium frequencies. So we get the highest ratings when there are ripples only at high frequencies, and that we took that into account later on in our modelling approach. This is showing the effect of spectral tilts, and as you can expect, if you have spectral tilts over a wide frequency range, shown here, and they're large in absolute value, either minus 1 dB per cam or plus 1 dB per cam, then you get a large degradation in quality. But moderate spectral tilts don't have too much effect, even when they occur over a wide frequency range. And finally, this is looking at the effects of band limiting. So here we're looking at the effect of removing the lower frequencies. We're increasing the lower cutoff frequency from 55 up to about 300 hertz. And on this dimension, we're looking at the effect of decreasing the upper cutoff frequency from about 17,000 down to 3,500. And you can see that removing either the low frequencies or the high frequencies degrades performance, and you get the worst performance when you've got the smallest frequency range possible, which is from about 300 up to 3,500. That gets an average rating less than 2, and that's what you typically get through a telephone or a mobile phone or a landline. That's the frequency range you get. So though just the limited frequency range gives pretty lousy sound quality, and you'll notice that the lower cutoff frequency has a slightly bigger effect for music than for speech. For speech, it's not too critical to have those very low frequencies in, but for music, it's much more important. And up here, you can see a bigger effect of these limiting the low frequencies. Incidentally, this box right here is what you typically get with a hearing aid. Hearing aids typically amplify from about 200 hertz up to about 5,000 hertz, and so that also gives pretty low sound quality. Okay, so I want now to talk about the general principles of how you might predict perceived quality using auditory models. And the general approach is to create some kind of internal representation of a test signal for a completely undistorted test signal, and then to generate a corresponding internal representation of the distorted signal after it's gone through the device that you're interested in, and to quantify the difference between those internal representations. And we think that perceived quality can be predicted from that difference. The bigger the difference in the internal representations, the lower is the quality. But depending on exactly what the measure is, you may need to have some nonlinear transform to get directly to the ratings of the subjects. So in our approach, to predict the effects of linear distortion, we didn't consider the temporal fluctuations in the sounds at all. This is purely based on steady state properties of the excitation patterns evoked by the sounds. And it doesn't matter critically what kind of input you use, but in these studies, we found that a pink noise seemed to work quite well. This is just a noise whose spectrum level goes down by 3 dB per doubling of frequency. And roughly, that's got a constant level per Erb. That's not quite true, but it's roughly true. And so we put this pink noise through the device under test with a target response that might be flat for a loudspeaker or a diffuse field response for a headphone. And we calculate the excitation pattern after passing the signal through the device that we're testing. We sample the excitation patterns at 0.5 cam intervals, and I use I for the index of the Erb number. That's just that you're counting along in steps along this Erb number scale, and I is just the index of the Erb number. And we can denote the excitation level evoked by the original signal as EO with index I, and the excitation level evoked by the distorted signal as ED with the index I. And we calculated 2 measures of the overall difference in the excitation patterns. And one was just the standard deviation of the values of the differences across all Erb numbers. So that's just you take the difference between the original and the distorted excitation pattern, and you work out the standard deviation of that across all Erb numbers. And we found that that gave reasonable predictions, but it didn't capture all of the effects in the data. And we wanted to capture the effect that high density ripples have a somewhat bigger effect than low density ripples. And to capture that, we also used these second order excitation pattern differences, which are to do with the rate of change of excitation in the pattern. So we're looking at the difference in excitation between 2 adjacent Erb numbers, and we compare that difference for the original and the distorted signal and look at the standard deviation of that. So we have these 2 measures, and we take a weighted sum of those first and second order differences, but we found that we got better predictions if we used a frequency dependent weighting with less weight for these higher order, the second order differences for very low and very high frequencies. And that gives us our overall weighted excitation pattern difference D. We found out that the relationship between D and the subjective ratings was an inverse one, as expected. The larger the difference, the lower the rated quality, but it was a slightly curvilinear relationship, and we simply fitted a simple function to that relationship in order to generate predictions. And this shows this compares the obtained ratings that we got and the predicted ratings for all of the different conditions in our experiment. The ratings for music on the left, the ratings for speech on the right. The correlation in both cases was 0.955. Now, these ratings were gathered in 2 separate sessions, and if you look at the average rating for the first session and the second session, the correlation was about 0.95. So basically, we can't expect to do any better than this. These predictions are essentially perfect. So the model can do very well for these artificial types of distortions. Now, we also extended this to do some measurements with real linear distortions, and we did this with 2 types of transducers. One was telephone transducers. This was a project that was funded by Nokia, so naturally they gave us a whole bunch of telephone transducers, and we put signals through those transducers, and these are the ratings we got for those, which were all pretty low as expected. And we also had a bunch of high-quality loudspeakers. Now, we didn't use the actual loudspeakers. We used their measured frequency responses and simulated those with digital filters, because we're not taking the effect of room acoustics into account in any of this. But these mostly had a pretty flat on-axis frequency response there. The price of these ranged from about $2,000 per loudspeaker up to $10,000. But they all cluster together in a small group. They're not noticeably different from one another. But you can see that we're able to predict the effects of the linear distortions produced by these transducers. And again, we get pretty good correlations here. Okay, so I want to now move on to talk about nonlinear distortion. And first of all, I want to describe an experiment that we did to evaluate the perceptual effects of nonlinear distortion to gather some data using different types of distortion. So we used various artificial distortions, but some of which can occur in electroacoustical systems. So one type of distortion was just hard symmetrical clipping, where you basically flatten the tops and bottoms of the waves. And you can get this in amplifiers if you overdrive them. Hard asymmetrical clipping, where you clip the positive peaks only. Soft symmetrical clipping. This is the kind of distortion that can occur in valve amplifiers, which some people actually like. Guitar players like the soft distortion produced by valve or vacuum tube amplifiers, but generally it's producing distortion which has undesired effects. Center clipping can occur in some badly adjusted transistor amplifiers. So these first types are all types of distortions that can occur in real electroacoustical systems. And then we had a final type of distortion that was very artificial. We wanted something that sounded really bad. And what we did with this was to raise the instantaneous absolute magnitude of the signal to a power alpha, where alpha is not equal to 1, but preserving the sign. So you might take the positive part of the signal, raise it to the power 0.5, and keep the sign positive. For the negative part, you would take the absolute value of the negative part of the signal, raise to the power 0.5, and then put the sign back again. So this sounds pretty nasty, especially when you have values of alpha that are a lot different from 1. Okay, so let's have a look at the results of that. So these are our mean ratings for speech. I'm sorry, this is a rather detailed slide, but we've got a very good quality projector here, so you can actually see the numbers. It's clearer on that screen than on mine. So this is showing the effects of hard symmetrical clipping. Clipping 0.5% of the time has almost no effect. You've got almost the highest possible rating. But as you increase the percent of time that the signal is clipped, then the ratings go down. And 10% clipping sounds quite bad. Soft symmetrical clipping has smaller effects, as you would expect. And this full range modification that I talked about really has the nastiest effects, and if you raise the instantaneous value to the power 0.5, or if you square it, then that really sounds very nasty and you get extremely low ratings. Okay, so I want to go on now to talk about how we model the effects of this nonlinear distortion. Now, nonlinear distortion has effects in the time domain as well as in the spectral domain, and so we think that to model that, you need to consider a time domain representation. The excitation patterns are not enough. And we can think of the signal at each place on the basilar membrane as a narrow band signal that we can decompose into a temporal fine structure and an envelope. The temporal fine structure is a kind of carrier, and an envelope is the slower fluctuations in amplitude superimposed on that carrier. And this, the fine details of the temporal fine structure are carried in the patterns of phase locking in the auditory nerve to individual cycles of the carrier, whereas the envelope is carried in the slower fluctuations in firing rate over time, although for higher envelope rates you can also get phase locking to the envelope. And that's just illustrated here. This is a simulation of the waveforms that you might see at 3 different places on the basilar membrane, here tuned to 370 Hertz, here to 1,500, here to 4,800. I've given the values of the Erb N for these 3 center frequencies, and this speech signal has been passed through simulated auditory filters with these 3 center frequencies. So this shows the raw waveforms, and the fine structure is illustrated by these oscillations here. We imagine you get spikes evoked in the auditory nerve at the peaks or close to the peaks in the temporal fine structure. And this is the envelope, the slower overall fluctuations that carry information. Now, nonlinear distortion can affect both the envelope and the temporal fine structure, and we think that both types of effects are important, and we want to take them into account in our modelling. And so to do this, we need a time domain representation of the auditory filters. And in this work, we used an array of gamma tone filters. These are filters, a number of people, they were originally described by Johannesma in the Netherlands to characterize the responses of auditory neurons, but Roy Patterson played a key role in developing them. Malcolm Slaney and others have also contributed to this. And these are linear filters that ignore level-dependent effects. Now, it's not clear how important level-dependent effects are, but I'll show you later on that we can do pretty well just with these linear filters. And this shows the magnitude responses of an array of gamma tone filters with different center frequencies. Here they're plotted on a log scale. For medium and high frequencies, the bandwidths of the auditory filters are approximately constant on a log scale, so these filters have the bandwidths equivalent to the equivalent rectangular bandwidth of the auditory filters, and on a log scale they look a little bit broader at low frequencies than at high frequencies. This just shows the time domain of a typical time domain impulse response of a typical gamma tone filter. Okay, so again, this looks horribly complicated, but the principles of how we predict the effects of nonlinear distortion are the same as I described previously for linear distortion. We're going to create an internal representation of the input signal for an undistorted signal and for a distorted signal. So in this pass over here, we're creating a representation for the undistorted signal, and in this path here, we're creating a representation after we've passed the signal through the device that introduces the nonlinear distortion. So we have filtering to account for the effect of the outer and middle ear, and we do that with a single finite impulse response filter with quite a lot of coefficients, which you need to get an accurate low frequency response. Then we use an array of gamma tone filters, each one Erb N wide, and we use 40 filters. and I use the index J for the filters in this case. So we're creating two parallel representations, and what we do is a frame-based analysis. So frame index is represented by I, filter index is indicated by J, and what we do is to actually calculate a cross-correlation between the frame I for the undistorted signal and frame I and the adjacent frames of the original signal. And the reason we do a cross-correlation is to allow for any time-dependent delay, any frequency-dependent time delay you might get in the nonlinear system. In some channels you might get a longer delay than others, so we can roughly time align the original and distorted signals before we start this whole process. But then to allow for frequency-dependent time delays, we calculate a cross-correlation and we look for the maximum of the cross-correlation. So at the end of this, we're taking the maximum value of the cross-correlation for each channel and each frame. And then we're doing a kind of summation across frames to get an overall measure of distortion that I call R non-lin. So we're using, just to summarize that, we use a frame duration of 30 milliseconds. We take the maximum value of the cross-correlation and the original, between the original and distorted signals for frame I and filter J. And this allows for any frequency-dependent time delays in the nonlinear system. And we get this overall quantity R non-lin, and the idea is that the higher R non-lin is, the better is the sound quality. So this is a kind of correlation-based measure. So high correlation is good, and so we're looking for a high value of non-lin to go along with high sound quality. So to model the effects of nonlinear distortion of speech signals, we use speech as the input, and for modeling the effects of nonlinear distortion, we use music as the input. So here we're using realistic input signals rather than artificial input signals. And again, we found that the relationship between subjective ratings of sound quality and R non-lin was somewhat curvilinear, and we fitted that relationship with a simple function. So we have these three free parameters, A, B, and C, that we use to characterize the relationship between the subjective ratings and our correlation measure R non-lin, and we use that to predict the perceived ratings. And we fitted those constants separately for speech and for music. And this shows the results that we got. Again, each symbol represents one type of artificial distortion out of all those types that you mentioned, that I mentioned, and we're plotting obtained ratings against predicted ratings for speech on the left and music on the right. And again, you see we're doing extraordinarily well here, considering that these are based on subjective data with some inherent variability. So I want to go on now to talk about how we predict the combined effects of linear and nonlinear distortion. Most transducers have both types of distortions, and we want to be able to characterize both. So what we do initially is to run the models for linear distortion and nonlinear distortion independently, and we get a score from the model for nonlinear distortion, we call S-lin, and we get a score from the model for nonlinear distortion, which we call S-non-lin, and then we combine those with a simple rule. One can be weighted more than the other, but the sum of the weights is equal to 1 to get an overall prediction of quality. And we found that we got the best correlation between obtained and predicted ratings when we set alpha equal to 0.3, which means that these nonlinear distortions have a slightly bigger perceptual effect than the linear distortions. We're more sensitive to the noisiness, the grittiness, the harshness produced by nonlinear distortion than we are to the small changes in the excitation produced by the linear distortion. So to test this, we did an experiment where we used various combinations of spectral ripples and different types of clipping, spectral ripples with full range distortion, spectral tilt with clipping, spectral tilt with full range distortion, band limiting combined with clipping or full range distortion. So lots of mixtures of different types of linear distortions and nonlinear distortions. And here's the results of that for speech and for music. You see that, again, we can get very good correlations between the obtained ratings and the predicted ratings. So, but this is all for artificial distortions. So I want to go on now to consider an experiment where we included both these artificial distortions and the real distortions introduced by transducers. So again, we used mobile phones and we had 4 different types of transducers with a variety of types of surrounding structures representing different types of earpieces. And we drove them either with a moderate voltage, which was within the specified range for the transducer, or we overdrove them. We drove them with a high voltage outside the specified range, say what they were distorting quite badly, giving more nonlinear distortion. And this shows the results. So the real distortions are shown by circles, the artificial distortions are shown by asterisks. The predictions here are not quite so good, but we're still doing pretty well. You'll notice that all of the real transducers get fairly low ratings, and that's partly because of their restricted frequency range. So even when they weren't overdriven, they still didn't sound that good because of their limited frequency range and imperfect frequency response. But overall, we can still get a pretty good correlation between the obtained ratings and the predicted ratings. And in fact, following this study, Nokia used this modeling approach to assess all of their mobile phones, not just new models, but every single phone that they made was checked by measuring its output and putting it through this model to see that it was within specification and was doing what it was supposed to be doing. So it did find a real application in that. So just to give you some overall conclusions, in sound quality evaluations, the sound as perceived by human listeners is the most important consideration. I think that's a point that came up in the discussion of the previous talk as well. And to predict the perceived quality as perceived by human listeners, we need to use models based on the way that the auditory system functions. And I've argued that linear and nonlinear distortion have different effects on perceived quality, and they need to be modeled in different ways. And the models described here lead to high correlations between obtained and predicted ratings for both artificially distorted sounds and for real transducers. And so I think there's room for more applications of this type of thing, but also these models need extending to take into account spatial effects and effects of room reverberation and things like this. But I think this is a useful start. And I'd like to acknowledge my collaborators in this work, particularly Chin Tuan Tan, who carried out most of the experimental work and played a key role in developing the models. So thank you very much.